Allora, well, um, let's go to our presentation here. And here now we have performed this operation of division, and now we are ready for defining our new state variable. Once we have obtained this proper function, this proper fraction for our aerodynamic matrix transfer function, now we are ready for defining our new state space variable, and the new state space variable are here defined by considering this quantity here. This quantity here. The fraction obtained as applied to the state space variable Q. And this quantity is the new state space variable defined like R vector. Our R vector is defined to be the following. We have also to include this, this multiplication factor like the dynamic pressure. So we have R is defined to be equal to dynamic pressure by the denominator SL U infinite I minus P minus 1 PR Q. Okay, so this is the key step. The key step is the definition of the new state space variable as equal to the obtained proper function multiplied by the state space variable. So write together this equation, and we have the following. We have two equations. Look, we have S square M plus K Q bar equal to dynamic pressure by A2 S square L square U infinite square plus A1 SL U infinite plus A0 and this is applied to Q bar R plus R, and consider that R tilde is defined to be equal to QD by SLU identity minus P to the minus 1 P R Q. Okay, so we have introduced just this definition and we have separated this part, but note that here you have a denominator. Remember, we had an integral. We had an integral and we have a denominator. Now, if you multiply this equation by this denominator, what you obtain? You obtain algebraically, you obtain this as L by U infinite identity minus P R equal to QD PR, P matrix, R matrix, Q tilde, and this formal multiplication is the transformation of the integral into a derivative. And so you have a polynomial multiplication on R, your new state space variable. So you are currently obtaining a differential equation for R, as we can realize just a few seconds later. Okay, so this is our new state space equation, and this is our new state space variable. In fact, now we are just to recap everything in time domain. You have to put together matrix. For example, here we have a matrix multiplying S square, and we have another matrix multiplying S square. We have a matrix, stiffness matrix, multiplying S to the power 0. We have a stiffness, but we have also a stiffness here. And excuse me, I forget to this R. This R. And so we have also R matrix plus QD R by Q. And so we have a stiffness contribution. We have a stiffness contribution here, here, and also here. And we have also a damping contribution by the aerodynamic. So we have a multiplication factor by S. So we have a damping matrix here. Excuse me. Oh no. Excuse me. We have a damping matrix contribution here, multiplying S. And so we can compact our mass, stiffness, and matrix contribution. In this definition, we have a general matrix of mass like M, the structural contribution, minus the contribution here. So you have minus QD by A2 L square by U infinite square. So you have this matrix. We have a damping matrix D sub C, which is equal by definition to minus QD A1 L divided by U infinite. And we have also a stiffness contribution given by the original stiffness, structural stiffness contribution, but we have also the contribution given by the aerodynamic, which is A0 contribution, and also R contribution. And in this compact form, introducing this global mass, stiffness, and damping matrix, our system is in Laplace domain given by S square MC plus DC S plus stiffness. And all this is applied to Q tilde, and we have equal to my plus R new state space variable plus the forcing term, and the R dynamic here is given by S L by U infinite multiplying R on the left hand side, And on the right hand side, I can write the other part, which is P R tilde plus QD P R Q tilde. Okay, eventually we can move this factor on the right hand side and write the following: S R tilde equal to U infinite by L P R. And we have also plus dynamic pressure U by L P R Q. And ladies and gentlemen, this dynamical system is composed by the dynamic of our structural variable Q, but we have also this new dynamic. This is the new dynamic given by the aerodynamics. And what about the state matrix of this new dynamic? The state matrix is exactly P matrix. In fact, if now we go back to the time domain, go back time domain, we have M C Q dot dot plus D C Q dot plus K C Q equal to R vector. Note that this vector is a function of time. This vector, we introduce this vector here, here, and the dimension of this vector, same dimension as Q. Okay, so in this kind of model for the unsteady finite state aerodynamic, we have an added aerodynamic vector with the same dimension of the state vector for the structural dynamics. The vector for the structural dynamic is the vector Q. Okay, so R has the same dimension of Q, as you can see here. R plus F. Okay, and the other system is R dot equal to U L P R plus QD U P R by Q. But if you are a really control system guy, you cannot you need to have a state space form for your dynamics. You want a first order differential system form, and therefore in order to have this, you can introduce the variable derivative of V, and so you can write Q dot is equal to V, and then here you have M C V dot, which is Q dot dot, is equal to minus D C V plus K C Q plus R plus F. This is minus, excuse me, minus. And the last equation is R dot equal to U infinite L P R plus QD U L P RQ. So, very close to the final result, we have V dot equal to, excuse me, Q dot equal to V, and then we have V dot equal to minus M minus 1. We are currently inverting, we are just putting this mass contribution to the right hand side, pre-multiplying by the minus MC to the minus 1, excuse me, and then we have the following. We have this by Kc Q minus M minus 1 D C multiplied by V, and we have plus M to the minus 1 by R, and finally plus M to the minus 1 F, and here we have R dot equal to QD U by L P excuse me, it's not here, 2D P by R, and the other term is plus QD U by L, U by L, QD PR by Q. In other words, in a state space form, we have the following. If we introduce the state space vector defined like Q dot and R in the MATLAB style, we have a state space matrix A, which is 3n by 3n. N is the number of modes, structural modes used in the analysis. And we have, look at the first equation here. In the first equation, we have V, and therefore it is V is the second location of your state space vector, and therefore we have 0, 0, identity matrix, 0. First equation. Second equation, we have something multiplying Q, and is this term here, so we have minus M C to the minus 1K, and we have minus C and C minus 1D, and we have M to the minus 1C, and finally the last equation here is something multiplying Q is this part, so we have QD U by L P R. Second term is 0, and the third term is U by L by P. So defining this metric in this way, we have X dot is equal to AX plus, what about the forcing term? The forcing term is only here, and therefore you have 0, M to the minus 1, 0, applied to F. And so this is the B matrix. Okay, are you happy? I hope so, because this is the aeroelastic system. In a state space 4. In standard space stays 4. And note that the matrix A, the state matrix, state space matrix, is a function of the flight parameter u infinite. You have u infinite here, here, and whenever you see here u infinite, you have the dependency on u infinite. You have the dependency on rho. You have the dynamic pressure here, and that's all. Okay, and you have an explicit dependency on this parameter, and then you can study the stability in a standard form, in the sense that one can study the stability in a standard form. And this is what I said here, and I promised to you. When you have this approach, the advantage is to describe the elastic system in a state form. Okay? And we did it. And this is the price we paid. The price we paid is the expansion of the state vector, including this new state space variable. This new state space variable is actually representing the dynamics of the aerodynamic, and the coefficient matrix associated to this new state space equation is as you can see here, is this system, and is this matrix. And note that this local dynamic given by the aerodynamic is regulated by P vector, and the P vector is the vector of the poles of our aerodynamic matrix approximation. Here is the denominator of our aerodynamic matrix. Okay. Okay. I want to expand this concept. Expand this concept to exercise number 2. I mean, to Theodorsian theory. I don't understand. Okay, keep calm. Take the exercise number 2 together. The exercise number 2 is the following, and we have this equation for the aerodynamic matrix. Let me take this equation, just a second. I want to take this, and I want also to take this, I want to take this. Please follow me with this point, which is another interesting point to be considered. Okay. This is our equation in the considering the Tudorson theory, and look, this is the lift and the moment as given in our Tudorson theory. We have the generalized force vector E1, E2 equal to a matrix applied to H and alpha. And this is exactly this equation. And here we have lift and moment as generalized force. Okay. Now, what's the problem? The problem is the following. We have this complicated function. We have an analytic quadratic function, maximum quadratic function in the state space, in the frequency. We have omega square, we have omega, we have omega, but we have also this evil quantity. This evil quantity is depending on the reduced frequency. Question: is it possible to approximate this function of k by an interpolating structure? Same question as before. If you plot the Tudorson function, you have as a function of k a real and imaginary part. The real part is going from a value. If you see the analytic value of the Tudorson function, you have the plot in your note. You have that the real part start from one value and decrease asymptotically to 1/2. And this is the real part of the Tudorson function. The imaginary part of the Tudorson function is something starting by 0, as all the imaginary part in physical problem. 0 frequency, 0 value for the imaginary part, and then it increase and then decrease to 0 asymptotically. And this is the imaginary part of the Tudorson function. So, following a very similar approach, but not applied to the global aerodynamic matrix, but only to the Tudorson function. And this is interesting because this approach was considered 15, 16 years before the concept of state space aerodynamic. So this approach was introduced in the 1450. And the concept was the following: can I approximate the Tudorson function? Yes, you can do this. And this is the polynomial, fractional polynomial approximation of the Tudorson function. This is the fractional polynomial approximation of Tudorson function. Of course, what about the coefficient 0.1, 35, 0.65? How can we obtain this coefficient? Same history. You can sample. There are indeed in the literature, in the technical literature, there was many tentatives for obtaining this coefficient. One of these probably is known by you. When you study control theory, do you remember the story of the slope of your frequency response function given by 20 dB on decade of frequency, or minus 20 or plus 14 or minus 14 because of the power of the polynomial is a first order or second order polynomial in the fraction? Do you remember the story of the slope of 14 dB by decade or 4 and so on? If you consider this method of seeing the frequency response function as a product of elementary bricks, elementary fraction of the first order with the time constant or coefficient given by the slope of this asymptotically value, 14 or 20, plus 20 or minus 20 if you have a pole also 0, plus if you have a 0, minus if you have a pole, and so on. So by this technique, this technique is useful for determining the coefficient of the approximation. Or you can apply an optimal concept as before. You can minimize the error between the polynomial structure and the data you can obtain by evaluating the Dodson function by the definition through the Bessel function. Okay, so this coefficient of the Dodson function may be determined again. All these coefficients can be determined, for example, by minimum error approach. Okay, at the end of the story, you can substitute, and note that here we have P and here we have K, but the motivation of moving from K dependency or P dependency is the theorem of the complex function we stated before. We can expand the domain of a complex function if the complex function is defined in a closed domain and in the complex plane, and therefore we can assume for the Dodson function this approximation, and now you know very well the meaning of this approximation. This fractional approximation is not only a pure mathematical approximation, it's something more. It's suggesting to us the fact that we are close to transform our integral differential system in a pure differential system, also in the case of the Dodson theory. This approximation in the literature, these were known in the literature. We're talking about 14th, 15th, Padet, French guy, approximation. And they understood for this special case that this was a mean for transforming the original frequency domain vision of the state aerodynamic in a time domain vision of the state aerodynamic, so allowing to a aerodynamic operator to be represented directly in the time domain, because we are able to perform the inverse Laplace transform of this function, because it is a standard fractional function. Okay, and now you have understood the meaning of finite state approximation. Also for Theodorsen theory. I mean 2D analytic theory. And therefore, if you go to the exercise number 2, when we and this is the system is presented, and the first question is compare the exact Theodorsen complex function CK written as a combination of Bessel function, like here. This is the definition of Theodorsen function. It's complicated. You have in MATLAB this Henkel function, and you have in MATLAB this Bessel function here. So you can plot the Theodorsen function in real and imaginary part, and you can compare with this polynomial Padé approximation that I gave you. Okay? And this is the first point. After this point, you can evaluate the flatter margin not considering this approximation, but considering the complicated dependency of the system on the Theodorsen function, and then implementing the recursive of iterative procedure that I showed to you past week. Okay, but now you are also able to rewrite, and this other point here, you are able to transform your system in a state space form. In considering this approximation, put this approximation in the system and define a new state space variable. In order, pay attention. You have to introduce in your system, and I invite you to do this without support at the beginning. You have to introduce an aerodynamic state beta. How? Look, here you have the multiplication of the Theodorsen function by the state space variable, but this Theodorsen function multiplied by the state space variable could be at the beginning directly a new space variable beta, like R before, like R. But the point is that this C is not a proper fraction, because the degree of the numerator is of order 2, and the denominator is the order 2 as well. So I suggest to you to do this polynomial division and consider the result of the division plus a proper part, and I suggest to call as beta the proper part by this. Okay, exactly we did before for the general theory. Okay, in this way you should have a new equation in the new variable beta, and at the end you should have a system of the 6th order. Why 6? Because we have the initial equation, which are of the second order in H, and you have two equations of the second order, and the two equations of the second order becomes in first order form four equations of the first order, having a state space variable, the state space variable, and the first derivative. So H dot, alpha and alpha dot, four state space variable and four equation. But you have a new equation in beta, and the variable beta should be beta equal to an expression with a fraction which is second order denominator. So second order denominator, when you go back to the time domain, is a second order time equation, which are two equations of the first order. So 2, 2, 2, 6. Sixth order. Okay? So you should have a unique system, first order system of six equation in six order parameter. And for this system, you can study again the stability in a standard way. So just considering the eigenvalues, eigenvector of your new state space vector matrix. Okay? So this other point are simplified points. For example, in this point here, I asked to you to have a very simplified case with ck equal to 1, but I will show to you this in detail in our lecture in the afternoon. So I want to stop here. I'm sorry for this delay, 5 minutes. And now we are able to understand completely the exercise number 2. We have concluded the exercise number 2 with this part of the theory, and we will continue this discussion in the afternoon at 2 o'clock, talking about a final refinement of exercise number 2, and we will go ahead with the general theory. Thank you and see you later.